The topic of today are reverberation time measurements with the XL2. Reverberation time, or RT60, is a predominant indication of the acoustical properties of a room. It has a direct impact on the speech intelligibility within that room, on the level and distribution of sound, or the annoyance of background noise, for instance. So the purpose of an RT60 measurement is not only to identify these room characteristics, but also to be used for optimizing the reverb time within the room according to the purpose. And to give you a concrete example, I have here a small table with recommended reverb times, starting with very low values, typically for a recording studio, going up to even several seconds, for instance, in a church. So depending on the application for which the room is intended, you may use these values, and you will find more on the internet. You may use these values for optimizing the reverb time in the room after measuring it. My name is Markus Becker, and sitting next to me today is Berno Nix. He will assist me during this webinar, mainly by answering to your questions. The topics that we have prepared for you start with a definition of the reverb time, followed by some information on sound sources and test signals, as well as specific aspects that need to be considered for a measurement. Then we have prepared a practical presentation. We will summarize what we showed to you and end the session with some application hints. The overall duration of the webinar will be in the range of 30 minutes, followed by more time to answer your questions. Let's start with the definition of RT60 reverberation time. It is a time that it takes for a noise signal that is switched off to decay by 60 dB. If we look at the sketch here on the slide, please notice that the y-axis, the dB axis, is logarithmic, and by doing that, the decay is linear. Physically, the decay would be an exponential curve, but by plotting it against a logarithmic dB scale, it becomes a linear curve. And this allows us to identify the reverb time. And in practice, this goes like that. First, we have to allow a decay of 5 dB from the moment when the stimulus signal has been switched off. And the reason for that is that we have to overcome the nonlinearities in this very early time after switching off the stimulus signal. On the other side, we have to obey the noise floor that is present in the room, and we have to apply a headroom, a safety margin above that noise floor. So the range in between is the one where we can measure the decay of that sound signal. And we do that by applying a linear fit. You see that here by this red line, straight line that we fit into that decay. And that is the base for our calculation. Well, if you sum up all these values, the 5 dB decay, the 10 dB headroom, plus theoretically the 60 dB decay that we would need for a complete measurement, this sums up to a very high starting level of the noise signal, and this is hardly feasible in reality, in practice. And for that reason, we are actually using the T20 or the T30 data. So that means, for instance, talking about T20, that we just measure the decay over 20 dB from the moment we start the measurement, and we evaluate the time it takes for these 20 dB to decay. And by this value, we can calculate the RT60 result very easily by just extrapolating this T20 result. T30 is the same, just in that case we would wait for 30 dB decay and measure the corresponding time. Another important information is that the reverberation time is frequency dependent. And for that reason, you should always measure it with a spectral resolution, and actually typical resolutions are octave or third octave resolutions. Keep in mind the third octave resolution on the XL2 is only available if you have the extended acoustic pack installed on that instrument. Furthermore, when we talk about the stimulus signal that starts or stands at the beginning of our measurement, you can use 3 different types. We can use a loud bang, we can use a pink noise, or a chirp, which is a logarithmic glide sweep. The XL2 can cope with all of these 3 different types of stimulus signals, so it does not matter which one you choose for your application, for your measurement. Let's take a look at typical sound sources to generate such a loud bang. For instance, we have a starter pistol, or we could use a balloon that is bursting, or these clapping planks. These are just 2 wooden planks with a joint, and then holding them in your hand and clapping them together creates a loud noise, and that can be well used for RT60 measurements, at least in smaller rooms. When we talk about the balloon, there is a trick to even increase the noise that is created by the burst, and that is if you fill the balloon with an explosive gas and you ignite that. This is not always applicable, but in every room, but this is a nice trick to increase the impact of that bang. Well, the advantages of these solutions are they are quite lightweight, they are small to carry around. Keep in mind when you execute measurements that the noise that you create with either method has to be high enough, the level has to be high enough also at low frequencies. I will show you in a minute what that means and how you can verify that, but this is a challenge that applies for any of these types of generating a loud bang. And if we talk about starter pistol, for instance, there may be some places, some public places, for instance, where it's not so recommended to use that item. Let's say, for instance, in a church or in a kindergarten, that might cause some troubles if you walk around with a gun in your hand. So maybe this is not the best choice to do it in such places. In any case, very important, please keep in mind to protect your ears during the test. These bangs really need to be very loud to allow a decent measurement, and that means you have to wear earmuffs to be sure that your hearing perception is not affected. The alternative would be using a dodecahedron, a dodec as we call it, or omnisource. So this is an omnidirectional loudspeaker that can create, for instance, pink noise or a chirp, which is a logarithmic glide sweep signal. The advantage of this solution is that it's widely acknowledged, it's a proven method, it is unsuspicious, nobody would look awkwardly at you if you carry that around. Same as before, please make sure that the device that you're using is able to generate enough power, especially at low frequencies. This is always a challenge. And on the negative side, maybe it is, of course, a little bit more heavy and larger than, for instance, a balloon that you carry around. So the dodec together with the amplifier that you need takes some weight, of course, and size. Same as before, please obey the loudness that is created by this device. So here as well, you should carry good earmuffs to protect your ears during the test. Some specific aspects of RT60 measurements: you have to obey the environmental conditions, the noise floor of the room. The standard 3382 requires that maximum 2 persons are present in the room when you execute a precision measurement. However, still there will be some noise around in any room, so this noise floor gives you the base for calculating or for evaluating the required sound level of the stimulus signal. And the difference of what is achievable from the noise floor to the maximum level you can create allows you to decide whether only a T20 measurement can be executed or whether you can do a T30 acquisition. Talking about the signal source, it must be powerful in any case, regardless which type of stimulus signal you generate. The signal source must be powerful enough to thoroughly fill the room with enough energy over the whole frequency bandwidth. And this may be quite challenging, especially when we talk about very large rooms. In such cases, you may use several omni sources, several DODECs that are installed in the room and that are driven in parallel with the test signal. In that case, keep in mind that these DODECs should be placed randomly over the room at different heights, different positions. And another hint, when you use the chirp signal, the glide sweep signal, then you have the advantage that the sound level may be a little bit lower than if we would do the same test with a pink noise signal. That is an advantage of the chirp signal. Talking about the measurements, it is important that the microphone, the measuring microphone, must be placed in the so-called diffuse sound field, which means it has to be far away enough from the sound source, typically several meters. I will tell you more about that on a later slide. Then, if you have placed your sound source in a specific position, you have to measure the room reverberations by moving around with your test instrument as well to different places in the room. And when you measure with pink noise, then you have to repeat each measurement per position at least 3 times and average it. I will say more about that as well later. And that is due to the random character of pink noise. Well, we are at the point where we can start our presentation. I have here an EMA Pro, which is generating the test signal. The EMA Pro is connected via an amplifier to my DODEC. As test instrument, I'm using an XL2, and I have connected this XL2 via USB link to my PC to allow you watching the screen contents of the XL2. The USB link is not required in reality when you execute a measurement, but for the purpose of visibility, I have just connected it to my PC that allows you to watch what is going on. The test signal that I am applying is a pink noise signal with a cycle time of 3 seconds, and this signal is available by default on every Minirater. Here you can see now the noise floor that is measured by the XL2, and we will now start to adjust the settings for our measurement. The first one is by turning the jog wheel on my XL2, I can move the cursor here to the bottom left corner to the range setting, and it is important that the input range of the XL2 is adjusted properly to the expected signal level. You have to avoid under any circumstance that the device, the XL2, would clip, so the range must be high enough to be sure that you're not clipping the incoming signal. On the other side, you should rather choose a lower range if possible to increase the measurement accuracy. The next selection I can switch here between octave and third octave resolution. The third octave resolution, as mentioned before, is only available on the with the EAP option. Then the next selection I will do, I press this Set Level Markers button, and that now you can see here these gray bars. They indicate to me how loud my sound source must be over the full spectrum to allow a reasonable measurement of RT60 in the corresponding bands. Now I can decide whether I want to go for a T30 measurement or a T20. You see the bars become smaller with the T20 measurement and a little bit larger with the T30 measurement. Well, I will go for this selection and start my measurement by pressing the play button on my XL2. And you can see down on the bottom right corner that now the instrument is armed, which means it will wait now until a very loud noise is coming in. The instrument automatically recognizes that noise and will automatically start the measurement as soon as that sound source is switched off. Maybe you have noticed that these ticks in this upper line. These ticks indicate that for the corresponding third octave band, the measurement has been executed successfully. The lowest band, the 50 Hz of the third octave band, however, has not been measured successfully, and the reason is, you see here we have a pretty high bar, which means there is apparently some hum, possibly from the air conditioner in that room. So the sound source was not able to exceed this minimum level that is required for executing a correct measurement, and for that reason here this lowest band has not been measured successfully. Now we can toggle the screen on the XL2, and this is, by the way, also possible during the measurement. And here we see the result that we have acquired. By moving the cursor to the cycle button, we can now investigate the individual results from each cycle. The last one, the first one, second, third, fourth. Oops, as you can see, something has happened here that is a clear difference to the previous cycles. Actually, I have clapped in my hand, so I do not want to have this cycle as being part of my overall result, so I delete it. I move the cursor here, press delete, and it disappears. So remains the 4 cycles that have been quite consistent during my measurement. Second, please obey when we identify or when we look at the individual cycles. You see in the top line correlation. This is an indication about how good the linear fit could be applied. I will show that to you on a slide just in a minute. And secondly, by going into the overall result, the average result, you see the uncertainty, the measurement uncertainty, and that is displayed same as the correlation for each individual third octave band. So by placing the cursor here, we can step through all the bands and look on the corresponding results. So we see the RT60 result at 0.7 second, the uncertainty of 15.8% for the 250 Hz band. And the uncertainty is also displayed visually. If you look at the result down here, we have a horizontal black line, which is the average of my measurements, and the grayed part around that, that's the uncertainty. So the actual RT60 time is somewhere between these upper and lower limits. So let's get back to our presentation and summarize what we have just seen. First, we installed the stimulus signal source and made sure that it is loud enough for our test. Second, we adjusted the input range of the XL2 so that no clipping occurs. Third, we selected the spectral resolution. In our case, it was a third octave spectrum. We may set the level markers to visually verify whether the sound source is loud enough in all the bands that we want to measure. Then we chose the acquisition mode. In our case, it was the T30. We pressed the play button to start the measurement. And then we toggled between these two screens. Can be done at the end of the test, can be done during the test. So that gives us the feedback, first of all, whether the corresponding bands have been measured correctly. Second, the uncertainty of the measurement, and we also were able to take a look at the correlation for the individual cycles. If necessary, we can delete corrupted cycles that we do not want to have to be part of our overall result. So one of the most frequently asked questions is, what is the meaning, what is the difference between these two terms, correlation and uncertainty? I want to explain that to you here by showing this sketch. Correlation is an indication of how good this linear fit meets the decay curve. You see the black curve, this is the actual decay, and the green straight line is the linear fit that the instrument calculates automatically that shall represent the decay curve. Here we have a pretty high correlation. However, it may happen that for different reasons, for instance, if the room is very unsymmetric, that the decay curve is not that linear, is not that straight, but it has some curves, some distortions, whatever. So in this case, it's very difficult for the instrument to find an exact linear fit, or saying it the other way around, the instrument realizes that the linear fit is not correlating as good to this actual decay curve as in the first example. And this correlation is expressed in a percentage. The higher the percentage, the better. On the other side, the uncertainty is a calculation that is specified by this standard, and there are three parameters that go into that calculation. First, the measurement bandwidth. So a higher bandwidth, octave resolution for instance, gives us a lower uncertainty compared to third octave. The second parameter is the measured reverberation time. Here it is that the longer reverberation time, T30, provides better, lower uncertainties as T20. And third, the number of measurement cycles, which has to be minimum 3 to allow the calculation of an uncertainty, can be more. So the more cycles you measure, the lower, the better becomes the uncertainty. This leads us directly to the second question: how many measurements have to be executed? The standard requires for precision measurements minimum 3 cycles if you are using the pink noise stimulus signal. We would extend that recommendation to say that you should acquire as many cycles as are needed to get this uncertainty below the requested threshold. On the other side, if you are testing a loud bang or a chirp signal, then it is sufficient to just acquire 1 measurement per position. Of course, supposed that this single shot measurement is okay for all the bands. And another question that we hear frequently is, how can we visualize the RT60 results that we have acquired on the XL2? And the answer is quite simple. This data will be logged on the instrument, will be saved on the SD card of the XL2, and from there you can very easily transfer it to your PC and visualize it there. I'm going to show that to you. First, I show you the contents of such a log file that is written in a text file format, so it can be opened by any editor. You see here the information of the test instrument, the settings, the date and time, and here the individual RT60 results for the corresponding third octave bands and the related measurement uncertainties. And down here we see the cycles, the number of cycles we have executed, again with the T30 result in this case and the corresponding correlation. And this text file can be very easily imported into Microsoft Excel, for instance, or any other spreadsheet calculation program. You see here it's exactly the same information that we have here, but now with a few clicks it's very simple to visualize these 2 rows of data into a bar graph, into a chart that shows the bars, the RT60 results for the corresponding third octave bands. and down here are the measurement uncertainties. And you see here, this is a very typical result, that for the lower frequencies you have higher uncertainties than for the upper frequencies. Let's get back to our slideshow. Some application hints. First of all, the recommended measurement position. When you move around within the room from position to position, please keep a distance of minimum 2 meters apart from each other. Furthermore, please obey that the microphone has to be placed minimum 1 meter away of any reflecting surface like the floor, the wall, or the ceiling. And what is very important, that the minimum distance from the microphone to the sound source has to be in the diffuse field. And you see here a formula, but first let me explain what I'm talking about. The signal source creates a direct sound that is radiated towards the measuring microphone. And then you have a lot of reflections. I just draw some schematical examples in here, and these reflections sum up also in a certain sound pressure level at the microphone. And the diffuse field starts there, where these reflected sounds are higher than the direct sound from the signal source. And that is where you have to execute the measurement. So outside of this schematic circle around the signal sound source. And if you want to calculate that distance, you can apply this formula. So you have to take the volume of the room and you have to divide it through the speed of sound expressed in meter per second multiplied by the reverberation time. Then you take the root square out of that and you multiply it by 2. But if that is too complex for you to do that on spot, or if you do not know the exact volume of the room, for instance, just keep in mind several meters distance between the signal source and the measuring microphone is what is recommended, and then you are on the safe side. Second part, executing the measurements with the signal source at different positions. What you have to obey is when you shift the signal source from one position to the other, please do that in a kind of a random way. Do not move them around symmetrically, but rather look for asymmetric positioning in the room. And same as for the microphone, keep a decent distance between the signal source and the next reflecting surface. And the third and last recommendation that I can give you is to obey the impact of an audience, which means that you are measuring RT60 in the empty room. This is required by the standard, as I mentioned before, maximum 2 persons being present. Well, if you fill that room with people, if an audience is present, many persons, they would absorb the sound, and that lowers the reverberation time actually in that room. So when you measure a certain value, you can be sure that the room, the same room with some people inside, will have a lower RT60 value. Well, I'm at the end of my slideshow, and if you have any further questions or support demand, please contact our partners worldwide. Here we have just listed our subsidiaries. We have many more partners in all relevant countries all over the world. So please do not hesitate and contact us. We'll be happy to support you.